So far, we've taken a look at partial derivatives, like partial first derivatives, but can you take second derivatives when you're dealing with multivariable functions? Let's take a look here at this definition. If a function has two variables, then we know that the partial derivative with respect to x and the partial derivative with respect to y are also going to be functions of two variables. We kind of saw that up above when we created formulas here that contained x's and y's after doing the partial derivatives. So it's entirely possible then that you could go and take another partial derivative. But there are a couple things to make note of here. If I had started with a partial derivative with respect to x, I could then, for the second time I take the derivative, do it with respect to x again, or swap and go with respect to y. And it's the same thing if I would have started with respect to y. These are referred to as the second partial derivatives of f. And note, there are four possibilities. Again, what we have down here is some different notation. The most common notation that you're going to see us use is this notation right here. Okay. The first letter that's listed there indicates what you should take your derivative with respect to for the first partial derivative, and then the second letter tells you what you should do for the second partial derivative. All right, let's go ahead and actually try this out when we take a look here at example number 4. Let's take a look. How can I compute each of these if this is my function? All right, so the first thing we'll have to do is start by computing our partial derivative with respect to x. So I'm going to treat x like a variable and y like a number. If that's the case, then you'll note here I'm going to get 2x times a y squared for the derivative of my first part. And again, if x is the number and y is the variable, I'm going to get minus y times the cosine of x squared times 2x. I have to make use of the chain rule here. Okay. For my fy, my partial with respect to y, I'm going to treat y like the variable and x like the number. So here I'm going to get a 2x squared times a y, using just a basic power rule. And then over here, I'm going to get something really simple, just a sine of x squared. That's kind of like the coefficient on the y, and so that's all that's left after I do the power rule. So now, in order to get my different second order derivatives, I'm going to have to go ahead and take f of x and take its derivative with respect to x another time. When I do this, again, I'm treating y like the variable. So here, notice I would get 2y squared. At the back, things are going to get really ugly because I'm going to actually have to go ahead and use a product rule because I have stuff with x times stuff with x. I'm going to use this stuff here as the first part of the product and 2x as the second part of the product. When I do this, let's see, I'll do y times the cosine of x squared. I'll leave that alone and just take the derivative of the red stuff. And then I'll add and reverse the order. If I take the derivative of y times the cosine of x squared, that's going to be y times a negative sine of x squared times 2x. Notice I just put that negative out front, and I'm going to change that now to a minus. And then I'm going to have to go ahead and multiply by the full 2x. That was the red stuff. So notice that this 2x at the back is from the red, and this 2x is from the chain rule that came from the derivative of the blue stuff. All right, I'm not even going to simplify it up any further than that. I think that's perfectly fine. I'm now going to go ahead and try to compute my f of y. We'll go ahead and do that. Partial derivative with respect to y twice in a row. Okay, so let's see. If I took the derivative here with respect to y, notice that this is super easy. Again, y is the variable, x is going to be a number. I'm just going to be left with 2x squared minus 0. That's it, right? Because all this back here is just a number. So this derivative is super easy, at least way easier than this guy. Well, what's going to happen when I start doing like the mixed partial derivatives, right? So if I went back to x, but I took its derivative with respect to y. Well, let's see. Here I'm going to end up with taking the derivative here with respect to y, so y is my variable. I'm going to get 4xy, and then I'm going to get minus, and it looks like I'll just have 2x times the cosine of an x squared. If I do partial of y with respect to x, I have to again treat x now like it's the variable and y like it's the number. So that's going to get me 4xy at the front, and then I'm going to have to do cosine of x squared, chain rule, times a 2x. So this is how I can easily compute these. Again, dealing with the partial derivatives isn't too bad as long as you're able to successfully treat x or y like it's a number. That's kind of the weird part. It makes you kind of squint a little bit as you're looking at these things and trying to understand how you take its derivative. But with some practice, you'll get really good and really fast at this. Okay. One thing that's kind of interesting to note here is that these derivatives actually ended up exactly the same. And we're going to talk about why that's the case in the next theorem. Before we do that, though, I want to go ahead and try to think here about what these second derivatives might represent. We know that the first derivatives, based on where we started this section, represent slopes of tangent lines along different curves on the surface, whether those curves run parallel with the x-axis or the y-axis. Second derivatives should represent something pretty similar to what we dealt with back in Calc 1. And do you remember, what did a second derivative represent back in the Calc 1 class? They represented concavity, right? Or at least that's what we use them to help discuss. So actually, my fxx and fyy, these are going to help deal with the concavity of those different curves that exist along the surface in those different directions. So again, if I have some sort of a crazy surface floating out in space and I have a point, I have curves that maybe are going one way along the surface and curves that are maybe going another way along the surface. And so if I take the second derivatives, like fxx, that's going to be dealing with, say, like the red curve, where my y would always be fixed. That's going to tell me about the concavity on the red curve. Whereas fyy is going to be telling me about the concavity along the blue curve. The weird thing is what the mixed partials are doing, which is this fxy and fyx, right? What are those guys actually dealing with? What's kind of interesting is that those are going to be kind of telling me something about the tangent lines and how they change, but not with respect to the same direction of motion. I'm going to go ahead here and pull up a little applet with this link here, well, a little video with this link here to try to help see exactly how this sort of thing works. All right, so if you followed that link yourself, you'll be able to see that you get this sort of a graphic. What's kind of interesting here is you can see that what I have is I'm moving along, say, like this line right in here, or maybe it's like this line, right? This sort of a curve. And what's happening is I'm looking at this black line, which represents tangent lines along my different curves that go left to right. So look at all the grid lines that go left to right. Okay. And imagine as you're moving across those how you would draw tangent lines on them. On this one, maybe you'd have a tangent line that's like pretty steep and going really high on the left to really low on the right. Your tangent lines in the middle are going to be pretty flat. If you got to a curve here at the end, notice it starts really high and dips really low. So a tangent line on there should also start really high and dip really low. So what you actually end up with here is this kind of changing black tangent line. This black line here are tangent lines at the different horizontal, that is left to right, curves that exist along this surface. So when you compute something like fxy, you're looking at how the tangent lines will change their slope as you kind of skip to the next possible function that runs in the same direction. It's a little bit tricky here to see because we can't quite draw on this picture, but again, if you're looking at the curves along the grid lines that run left to right here, those are kind of the different functions that exist running parallel to, say, the y-axis here. And so here I'm looking at how the tangent lines on those are changing as I kind of jump from one to the next as I go from front to back along the surface. Okay, so that applet is kind of a weird thing. It kind of illustrates that there are some things that this fxy and fyx can tell us, but they are a little bit kind of strange, strange to kind of see. Okay. All right, let's go ahead and return to this idea that we had seen that these mixed partial derivatives here actually came out to be the same answer. And what we want to know is, does that happen all the time? Is that just a coincidence? Like, what does that have any significance to it? What's going on there? Okay, here's the theorem that becomes really, really interesting for us, and we'll return to later on in the course. Suppose that f is defined. That is, my function is defined on some set of x, y, z, or some set of x, y values, excuse me, down here in like the xy plane, right? So imagine there's like some disk of x, y values down here where I know the function exists above that. Okay. Well then, if that particular disk contains AB, so I know that the function is defined on AB and stuff around it. Then, if it's the case that f of xy, or fxy and fyx are both continuous functions on that little disk, well then it must be the case that they have to come out equal. So this is kind of interesting. So if you looked at the mixed partials, if they represented continuous functions, then they would have to be equal. Notice here, though, what I have at the start is a function that should by itself be continuous because it's only built from continuous pieces. And indeed, the functions that I end up with at the end here are also certainly continuous. The theorem says if those two things are continuous, they must end up being exactly the same. And so this is why they do indeed come out the same in this question. That's kind of cool. Those functions here, as I state in the note, were continuous all the time on all of R2. We'll be able to come back again, as I said, later in the semester to use this idea again in some other new contexts.